So there are several methods we will discuss one by one. Let us start from this 1/4 decay ratio criteria. Let us first discuss this 1/4 decay ratio criteria, which is typically used for controller tuning. Now for this tuning method, let us adopt the transfer function for the process. You see Gp, that is written Kp by tau Ps plus 1. It is basically the transfer function of a first order process. Controller transfer function is given in terms of Gc, and Gm, Gf, they are equal to 1. Now, if we substitute these individual transfer functions in the closed loop transfer function CLTF, we get this form. If you substitute these 4 individual transfer functions in the CLTF, we get this form. Can you quickly tell me the expression for tau and zeta? Let me know the expression for tau and zeta. Anyone got expression for tau and zeta? Three 0023 Siddhant. Are you there, Siddhant? 30023. 30027 Vivek Sureka. Are you there? Vivek. 30017 Sion Hallar. Are you there? Anyone got the expression for tau and zeta?
Sir, I am getting tau as root over tau p tau I by kpkc.
Correct. And got zeta?
So finding
What's your roll number?
19CH30029.
Anyone else got? You see, these are the expressions. These are the two expressions we get. Now let us come to decay ratio. You see, the title is saying that 1/4 decay ratio. That means decay ratio is equal to 1/4. That we will consider. So what is the formula for decay ratio? You see, this is the formula for decay ratio. This we have derived before. Exponential of minus 2 pi zeta divided by root over of 1 minus zeta square. Okay. Now, as I mentioned, the title is saying that decay ratio is equal to 1 by 4. Let us write then the expression for decay ratio. See here in this decay ratio expression, we are just going to substitute zeta expression and equal to 1 by 4. That's what I have written here. We are currently discussing the tuning method, namely 1/4 decay ratio. So this is decay ratio expression and that is equal to 1 by 4. Just substitute the expression of zeta inside this decay ratio expression and get the last form of equation shown in the slide. Fine. Now let us simplify this equation. Let us simplify this equation, last equation. Then we get this form. After algebraic simplification, we get this form of equation. After algebraic simplification, we get this form of equation. So we have one equation in our hand, but we have two unknowns. So it is underdetermined system. Okay, we have only one equation, but we have two unknowns, two tuning parameters, Kc and tau I. So we can have infinitely many solutions for this. So we will have several controller settings. Now let us consider this case Kp equal to 0.1 and tau p equal to 10. Let me tell one thing here, for a particular process for which you are going to employ one controller, for that process Kp and tau p are known to us. Note down this point, this is important. When you are going to consider a process for closed loop performance study, for that process Kp and tau p are known to us. Okay, that's why Kp and tau p, they are given here. Do not consider they are unknown, they are known to us. Okay. Now with this situation, we can have many sets. So here I have just calculated 4 sets. In fact, if you have one equation, two unknowns, in that case, you have to fix one parameter value and find another one. So accordingly, these 4 sets are determined. I have fixed Kc1, then I have determined tau p from that equation. Similarly, I have fixed Kc equal to 10, then I have determined tau I, like this way 50 and 100. For those two cases also we have determined tau I. Now question is which one we should select? That is the question. Which tuning set we would select. We have so many tuning sets. Now naturally one question comes in our mind, which set we should select. You see some guideline is given here. You first select KC so that PI has the necessary strength to push the response back to the desired set point. Then you pick up corresponding tau I value that satisfies 1/4 decay ratio criteria. This is the general guideline, but still we are in fact not that much satisfied with this statement as well. Okay, we cannot say that we will get the best performance by this way. Anyway, this is a 1/4 decay ratio criteria based on which we can tune the control parameters. So what are the drawbacks of this process? We have discussed 1/4 decay ratio criteria. I have detailed the process tuning method. Now can you tell me a couple of drawbacks for this process, student? Anyone? What are the drawbacks of this process? Tell. First drawback is no clear-cut guideline to choose KC and tau I. There is no clear-cut guideline to choose KC and tau I. And here we have considered PI, that's why only 2 unknowns. If we go for PID controller, we will have 3 unknowns. In the example system, we have considered PI, that's why we had only 2 unknowns, KC and tau I, that we need to determine based on one known equation. But if you go for PID controller, there are 3 unknowns, KC, tau I and tau D. So 3 parameters you have to determine based on only one known equation. It is applicable only when the closed loop transfer function is second order. If it is first order, there is no existence of decay ratio. Even for higher order, the same case we face. So this 1/4 decay ratio method is applicable only when the closed loop transfer function is second order. And another important point is that you see it selects tuning parameter values based on the response at only 2 time instants. If you recall the plot, this decay ratio is basically C by A. So C corresponds to 1 point or 1 time instant and A corresponds to second time instant. So we are basically plotting Y versus T, and despite having the entire response for the time period, we are just considering the performance or response at 2 time instant only. And based on that, we are trying to find the tuning parameter. I repeat, if you recall the plot for underdamped response Y versus T, from which we determined decay ratio. So in that plot, we are only considering the process response at 2 time instants. One corresponds to C, another time instant corresponds to A, because our decay ratio is C by A. So we have the entire response available, but we are only considering 2 time instants. So yeah, its accuracy is questionable. So that's it. Now with this gap, you can say, let us move to another better tuning method. With these drawbacks or gaps, you can say, let us move to another technique which is better than this. Our next technique is time integral performance criteria. Our next tuning method is time integral performance criteria. Let us first discuss what is the motivation of discussing this criteria. What is the motivation behind this time integral performance criteria? That we want to know first. So if you see the plot y versus t, there I have shown two performances, two responses. One response corresponds to tuning set A1. Another closed loop response A2 corresponds to tuning set 2. So we are basically using two tuning sets. One corresponds to KC1 tau y1 and second tuning set corresponds to KC2 tau y2. Now my question is, tuning set 1 provides something minimum. What is that? And tuning set 2 corresponds to also something minimum. What is that? Can you tell me, student? If I use tuning set 1, which one is minimum? Which criteria is minimum?
Time period.
What time period?
The tau.
What is tau? You just recall the criteria like, let me remind you, rise time, peak time, overshoot, decay ratio, settling time. Among these, you give the answer. In case of A1, which one is minimum? Rise time is minimum, you see. It is reaching first time, the ultimate response with a minimum time in case of setting A1. Now, can you give me the answer for tuning set 2 or A2? Which one is minimum or which one is smallest?
Sir, overshoot.
Overshoot is smallest. Now question is, I mean, here we have considered only two cases, minimum rise time and smallest overshoot, but there are few other cases also, like we may have minimum decay ratio, we may have minimum settling time. Okay. Now we are in dilemma, you know. Which one we should select? Let us consider only two cases, tuning set 1 and tuning set 2. Now we are in dilemma, which one we should select, criteria 1 or criteria 2? It's difficult to say. And you know, in both the cases, we consider the response at a particular time instant. So rise time corresponds to a single time instant. Overshoot corresponds to a particular time instant. Although the entire response is available in our hand, I mean they are available, but we are just considering the performance at a particular time instant. So definitely we cannot expect very good tuning set that can provide optimal closed loop performance. So I think you are understanding what I want to mean. We should choose a criteria that takes into account the closed loop response for the entire time duration. And that is taken care of by time integral performance criteria. We should choose a criteria that takes into account the closed loop response for the entire time duration. And that is taken care of by time integral performance criteria. Okay, so this is the motivation behind this time integral performance criteria. Now let us elaborate the criteria. Let us elaborate the criteria one by one. What are those? This is one such criteria, integral of the square error. So we are representing this by IAC. It is integration of error squared t dt. And here epsilon is error, and that is YSP minus Y. See, the upper limit of the integration is infinity, but that is actually the operation time. I mean, how long you are running the experimental setup, or how long you are running the industrial unit. So that is operating time. Okay, this is integral of the square error. This is one such criteria. This is another criteria, integral of the absolute value of the error, IAE. So it is also integration 0 to infinity. That is, infinity means basically the operating time. It is not actually infinity, and the absolute value of the errors. Now student, can you tell me why absolute value is taken here? Why absolute value is taken here? Anyone?
Sir, there might be positive and negative deviations. So the negative deviations will cancel the positive deviations.
Very correct. What's your roll number?
19CH10054.
See the answer. What he told, that is correct. So we should count both positive and negative errors. Thus absolute value we consider. And it is shown graphically also. Epsilon may get cancelled partly or mostly. That's why the absolute value is taken into account in this IAE criteria. Okay, now come to the third criteria. That is integral of the time weighted absolute error, ITAE. Our third criteria is integral of the time weighted absolute error, ITAE. So here what we do, we multiply the time t into absolute value of the error. So it is called ITAE, integral of the time weighted absolute error. In a similar fashion, we can consider also integral of the time weighted square error. Similarly, we can consider ITSE, integral of the time weighted square error. Okay, so these are our time integral criteria. Now, what is the objective? We want to any one of these criteria, we want to minimize any one of these errors. We want to minimize any one of these errors. So the errors we have considered IAC, IAE, ITAE, or maybe ITSC. You just take into account here any one as per the suitability. We are just going to discuss which one we should adopt among these. But anyway, let me clearly tell you that this is basically the objective function. And you can find out the controller tuning parameters. It may be only Kc, maybe Kc tau y, or maybe Kc tau y tau d. This is the goal of our current study. Now we have discussed a total 3 or 4 criteria. Question is which one we should select? Let us discuss that issue now. Guidelines in selecting the best criteria. Guidelines in selecting the best criteria that we want to discuss now. So at first it is written, if you would like to strongly suppress large errors, you go for IAC criteria. If you would like to suppress small errors, you go for IAE criteria. To strongly suppress large errors, you go for IAC criteria. And if you want to suppress small errors, you go for IAE criteria. But still, I am not understanding why this is so. Let us come to get the answer of this question, why it is so. Let us elaborate in this way. We have epsilon. We can consider either epsilon or epsilon squares, and then we select accordingly. I have suppose a small error 0.5. And in another case, error square, that means my error is becoming smaller further, because if we take the square, it is becoming 0.25. So which one is contributing more to the objective function? 0.5, because 0.5 is greater than 0.25. So we'll definitely consider the case which considers 0.5, because it gives more value to the objective function. That means based on which we are going to find out the tuning parameters, they will act more strongly than this one. Got the point? Let me again repeat. We have to consider which one is greater. So among these two values, 0.5 is greater than 0.25. That means I can say that this error term provides or contributes more to the value of the integral. So considering this larger value in the objective function, we get Kc tau y tau d that lead to provide strong control action compared to that considered error square term. So you remember like this way, which value is contributing more to the objective function, we should consider that. Because it is giving tuning parameter values which provide a stronger control action. Now you consider another case. Suppose our error is 2. So naturally error square is 4. So 4 is greater than 2. That means we will consider the criteria which takes into account error square, and that is IAC criteria. Okay. Here 4 is greater than 2. That's why we should consider the criteria which calculates tuning parameters based on error square in the objective function. That is IAC criteria. And another one left, that is ITAE. For ITAE, I mean when we consider ITAE, when we would like to suppress errors that persist for long times. So you try to understand this point. Let us first draw this figure which is shown in the right hand side. First you draw which is shown in the right hand side. It is y versus t basically. Here you write t, I missed it. This is y versus t plot. Okay. Now we have divided into two segments. One is AB, another one is BC. In this first segment AB, our error is greater than 1. And in the second segment BC, our error is less than 1. So if error is greater than 1, then error square is greater than error, which is written here. In fact, I have shown also before error is 0.5 and error is 2. In case of 2, if we make the square of it, it is always greater than error. So we should prefer IAC for segment AB. And for segment BC, we should prefer IAE. So we are clearly understanding that for segment AB, we can use IAC criteria, and for segment BC, we can use IAE criteria. But if we want to go to criteria for a particular process, it makes the formulation complicated. If we go to use two criteria for a particular process, it makes the formulation complicated. So that's why we should go for ITAE. Now, can you tell me why we should prefer ITAE? Still, it is not clear. Student, anyone? I have shown we can go with IAC plus IAE, but it makes the formulation complicated. So that's why it is suggested to consider ITAE, but why? Anyone can give the answer? You see the answer. As time increases, error decreases. So if we multiply time and error, it may contribute a large value to the objective function. As time t increases, error decreases. So that's why we want to multiply t with epsilon, so that it can contribute reasonably large value to the objective function. Yeah, that's it. I mean, this is a guideline. So if you have doubt, you can ask me. Did you understand?
Yes, sir.
Okay. Then go to the application part. How we can apply this time integral performance criteria, that we want to discuss next. So let me provide the sequential computational steps which we need to follow for controller tuning by using the time integral performance criteria. So for this, let us take one example with these transfer functions. We are currently discussing the computational steps involved in controller tuning with the use of time integral performance criteria. For this, let us adopt this process. So all 5 individual transfer functions are known to us: GP, GD, GC, GM, and GF. So for this, a couple of minutes back, I have shown this. In fact, I have asked you what is the CLTF for this process. So this is the closed loop transfer function. First equation, this one is the standard CLTF form. And if we substitute all individual transfer functions, we get equation 4. So in step 2, basically, we formulate CLTF, closed loop transfer function. First equation is the standard CLTF form. And if we substitute all individual transfer functions and simplify, we get equation 4. And tau zeta values are given here. Tau and zeta values are determined here, you see. Okay. Now let us go ahead with servo problem only. So servo problem means our D equal to 0. Let us tune the controller parameters just for servo problem, not for regulatory case. So accordingly, this is our CLTF. In the next step, we want to introduce a unit step change in set point. In the next step, we would like to introduce a unit step change in YSP. Okay. Now let us take inverse of Laplace transform. If we take inverse of Laplace transform, we get this equation. See, if you recall the time integral performance criteria, all time integral performance criteria requires the information of error. So for finding that error, we are basically trying to find yt. So if we take inverse of Laplace transform, we get this y expression. Fine. Now let us come to formulate the objective function. So we are adopting here say IAC performance criteria. I am just showing for a sample case. So let us adopt IAC performance criteria. It is basically integration of error square dt. So error means you know ysp minus y, and in place of y you substitute equation 6. In place of y you substitute equation 6. Fine. Now minimize the IAC with respect to zeta and tau. So just let us write differential form with respect to tau as well as zeta and make them equal to 0. So if we consider that, we get optimal values as tau prime and zeta prime, and they are shown in the next step, you see. So if you have here, IAE criteria, just replace IAC by IAE or ITAC by this. Here you write ITAC, ITAE or IAE, whichever is suitable for you. I am just showing for a sample case. So now we have two equations, we have two values, tau prime and zeta prime. Now these expressions we have obtained before. So we are just replacing in place tau by tau prime and zeta by zeta prime. Now we have two equations and two unknowns. Solve them and get optimal Kc and tau y values. We have two equations and two unknowns. Just solve them and find Kc and tau y. Okay. We have two equations, two unknowns, solve them and get the optimal value for Kc and tau I. If you go for PID controller, you need to differentiate with reference to Kc, tau I and tau D. So you can get three equations and three unknowns. Now see, I have shown how to use the IAC performance criteria. Now you can extend this concept to IAE or ITAE. And secondly, I have shown only for the servo case. You can also similarly proceed for regulatory case, but you note down one point. The tuning parameters set which you are getting based on servo performance, you will get a different set for regulatory performance. Note down this point. The tuning set which I have shown how to get for servo case, this will differ from the tuning set that is determined based on regulatory performance. Now you have to select for your process which one you are looking for. If you are looking for your servo performance, you proceed like this way. And if you want to suppress the effect of disturbance, in that case, you find the tuning set based on regulatory performance. So this is all about time integral performance criteria. In fact, this time integral performance criteria is extensively used in research purpose. In process control research, this time integral performance criteria is perhaps most widely used. Any questions, student? Otherwise, we'll go to the next topic. If not, let me ask one question. Can you tell me which variable in a chemical process we prefer for IA and which variable we prefer for IAC? Which controlled variable we prefer? I mean, IA is preferred for which controlled variable and IAC is preferred for which controlled variable? Can you give any example for chemical systems? So which control variable is usually very small, lower than 1? Any idea? Product composition. Distillate, like if you recall the distillation column, top product composition, that is mole fraction. So mole fraction is always less than 1. So this is the case for mole fraction, 0.5. Similarly, can you tell me which variable shows always greater than 1 value? Any variable? Answer is temperature, pressure. They are always greater than 1. So composition is one example, for which case we prefer IAC performance criteria. Temperature or pressure are two examples, for which case we prefer IAE performance criteria. I think you do not have any question. So let us come to the next method. This is a third tuning method. So here let us know what is again the motivation behind Cohen-Kuhn tuning method. That we want to know first. What is the motivation behind Cohen and Kuhn tuning method. So what we'll do, we'll first list the drawbacks of the processes tuning methods which we have discussed so far, and we will see at the end that whether Cohen-Kuhn method can overcome those drawbacks or not. I repeat, we will first list the drawbacks or limitations of the tuning methods which we have discussed so far, and at the end we will see whether those drawbacks we can overcome by Cohen-Kuhn method or not. This is the way we are going to discuss the motivation behind Cohen-Kuhn method. So let us start with Ruth test and Ruth Locus method. You see the 3 points I have written here. Both the methods do not provide exact tuning parameter value. They provide the range only. Within this range, closed loop process is stable. Outside of this range, the process is unstable. That much we can get. And that's why these two methods are better to call stability technique rather than tuning method. Fine. Ruth and Locus, they do not provide exact tuning parameter values. They provide only the range within which the closed loop process is stable. So that's why it is better to call them as stability technique instead of tuning method. Next, another method we have discussed subsequently, that is 1/4 decay ratio criteria. This is based on again closed loop response at few points. And this method yields multiple tuning sets. Today we have discussed 1/4 decay ratio criteria, and in this method tuning is based on closed loop response at few points, in fact based on only 2 points, and it yields multiple tuning sets. There is no clear-cut guideline for selecting this method. In fact, I have also mentioned other 2 drawbacks. I have mentioned today total 4 drawbacks. So you can put here all 4 drawbacks in fact. Just now we have discussed time integral performance criteria. So it has 2 limitations. It requires accurate process model. In other words, if process model is not accurate enough, do not expect good tuning set. Okay. So the performance of closed loop response depends on how accurate model you are going to use in time integral performance criteria for finding tuning parameters. Since model is involved, so computational complexity is there. So thus we are looking for an empirical tuning method, and that is process reaction curve method developed by Cohen and Kuhn. Thus we are looking for an empirical tuning method and that method is popularly called as process reaction curve method, which is developed by 2 scientists, namely Cohen and Kuhn. Now let us elaborate this method, Cohen-Kuhn method. So what is the procedure? I mean, what steps are involved in this method that I want to discuss first. Let us first discuss the procedure in details. Then we will see the application of this method with one example. So you see, in this method, the controller is disconnected from final control element. As shown in the block diagram, the controller is disconnected from final control element. In this process, the controller is disconnected from final control element. Okay, it is written here. Now let us find the transfer function for this process. So from the above block diagram, I can write this equation. I think there is no difficulty to get this equation. And Cohen and Kuhn, they have considered only this case. They have considered d equal to 0. And you see, this is called process reaction curve. This transfer function is GPRC. PRC means process reaction curve. Suffix PRC denotes the process reaction curve. And from this equation, it is clear that the process reaction curve depends on three individual transfer functions. One is for final control element GF, one is for process GP, another one is for GM, measuring device. Fine. Process reaction curve PRC depends on process dynamics GP, dynamics of sensor GM, and dynamics of final control element GF. Now you come to this third point. It is also shown in the block diagram that we are introducing a step change with magnitude A in C. It is also shown in the block diagram that there is a step change in controller output C with magnitude A. So it is simply, you see, C is replaced by A by S. In this equation, this C bar is replaced by A upon S, A by S. Okay, the same is shown in the block diagram also. Now, what is the observation of Cohen-Kuhn? You know, in this case, the process response we get for most of the chemical processes is sigmoidal in nature. This is perhaps the most important statement of Cohen and Kuhn. Or you can say this is the most important approximation they have made. Most of the chemical processes show the response of first order plus date time or sigmoidal response if we introduce a step change in C bar. This is the most important observation they have made, or you can say they have approximated. I repeat, if we introduce a step change in C, most of the chemical processes show the response of first order plus date time system. It is nothing but the sigmoidal in SIF. If this is the case, how we can represent it mathematically? We all know the first order plus date time system we represented by this transfer function. We have discussed before that mathematically the first order plus date time system, first order plus date time FOPDT system is represented by this transfer function. We have discussed this transfer function before. And in this transfer function, there are three parameters K, TD, and tau. And these three parameters we need to determine. How we can determine? Let us come to this graphical representation. I repeat, three parameters are involved here. So it is somewhat like this. If we introduce a step change in a chemical process, it shows this type of response, sigmoidal shape, you see, which is shown in this plot. Now this sigmoidal shape we can represent by this transfer function, first order plus date time transfer function. Now for this transfer function, we need to determine three parameters, K, TD, and tau, that we are going to determine now. Got the point, student? I repeat, you have a chemical process. You introduce a step change and you just plot the output versus time t. For most of the chemical processes, Cohen-Kuhn said it looks like this, sigmoidal shape. It is fine. Now this sigmoidal shape we can mathematically represent by this transfer function, first order plus date time. Now this transfer function has three unknown parameters, K, TD, and tau. You see they are noted here. So how we can determine these three parameters? That is our central point of discussion here. Okay, now let us first draw this figure, then we'll discuss how to determine these three parameters. K, TD, and tau. In fact, they are indicated in this figure. So B is ultimate gain, that you know. Now this is sigmoidal shape. So what we have done, we have just approximated first order plus date time. See, this is the date time part. We are simply separating this date time part from this first order response. See, this is the first order response. This dot dot, dot dot, then green, then entire fraction. And this portion is the date time part. Okay, so this is basically the transfer function order, transfer function of a first order plus date time. So let us divide into two fractions. One is first order, another one is date time. So this fraction is date time. I mean, this segment is indicating the date time part, and the rest part, you see this dot dot, then green, then continuation. This one is basically the first order part. And based on that concept only, I have written here tau. If you recall the first order system response, there it was t by tau equal to 1, here 1. So t by tau equal to 1 means t equal to tau. That's why it is written here tau. Okay. Now come to the determination part of these three parameters, how we can determine. You see, you can easily understand how we can determine these three parameters. K is the gain. So it is obviously delta output by delta input, B by A, tau equal to B by S, since S equal to B by tau, and Td is time elapsed until the system responded. Let me gist what we have discussed so far in this Cohen-Kuhn method. Suppose you have a chemical process. You just introduce a step change in the input variable, and then you see the nature of your output with reference to time. Cohen-Kuhn have approximated that this response, I mean y versus time, is sigmoidal shape, which I have shown graphically. Now this sigmoidal shape we can mathematically represent by the transfer function of first order plus date time. So first order plus date time transfer function has three unknown parameters, k, tau and td. Here it is shown how we can determine k, tau and td. Now interesting thing is that Cohen-Kuhn suggested some empirical relations based on this k, tau and td. If you know k, tau and td, you can easily determine the tuning parameters from these suggested empirical equations. All the controllers are function of k, tau and td. All the controller tuning parameters are function of k, tau and td. So this is all about Cohen-Kuhn method. In the next day, we'll discuss this method with an example. And now you can take a couple of minutes break. I will start the test from 11:20. This is Cohen-Kuhn method. You can ask me if you have any question. Else, you take a break for about 8 minutes and we will start our test sharply at 11:20. So student got my message. Test will start at 11:20.